Okay, so let's pick up the thread. We'll probably step back a little just because we are at a week-long break in between. So what we want to look at is study the equations for a charged particle moving in both electromagnetic and gravitational field. And mm, and we know that, like, if we are just looking at a motion of a charged particle in the gravitational field, then then that is given by the geodesic equation, and the geodesic equation is written out here: d2x alpha by d lambda squared plus gamma alpha beta gamma times dx beta by d lambda dx gamma by d lambda is 0. Okay. On the other hand, we also know how a charged particle would move in an electromagnetic field in the absence of gravitational field. Okay, so that is the equation like this, where acceleration of a particle is related to the external electromagnetic force, which is what is called the Lorentz force. And in the covariant form, in the Lorentz covariant form, this force is written in this particular fashion, where E is the charge of the particle and m is its mass, and f beta gamma is the electromagnetic field. Df gamma by d lambda is basically the velocity. Okay, so we know that these forces are velocity dependent forces. Okay, so natural generalization of the geodesic equation would be that in the absence of electromagnetic field, the equation looks like the ordinary geodesic equation. But in the presence of electromagnetic field, you would write down the geodesic equation as left hand side remains the same, but right hand side is no longer zero because there is some force acting on this charged particle. And remember that the Lorentz force equation is a tensorial equation, and therefore, if there is a force acting on the charged particle in some frame, then it is there in all other frames, and therefore, this quantity is necessarily non-zero if there is an electromagnetic field acting on a charged particle. Okay, fine. So we want to ask a question that how uh, how would this equation generalize uh, when you write it down in a, I mean, how do you make sense of this equation when we try to kind of study both electromagnetic and gravitational sources turned on? Okay, fine. So there was some exercise which was mentioned last time also, I think, where you can show that the equation of motion and Bianchi identity is the Bianchi identity, which gives you these two Maxwell's equation. An equation of motion gives you the del dot E and del cross B Maxwell's equations. Just an exercise to relate the covariant notation to the non-covariant notation. Okay, so we would like to ask what is the current density due to a charged particle, and every charged particle would be treated as a point particle. So if you have a large number of charged particles, we label them by some label n. En is a charge of nth particle, and it is located at a particular point xn, which of course would be time dependent. So this is basically the delta function is non-zero on the trajectory of the particle. Okay, the corresponding current would be the quantity which should be proportional to the velocity of the particle. So therefore, it's roughly the same expression times the velocity. And in the covariant form, we can write this current as summation over n En, and we write down four-dimensional delta function. And in the process of writing the four-dimensional delta function, you kind of, in a covariant form, you don't write dx by dt, but you write dx by d lambda, which is a parameter which parameterizes the trajectory, and you write x and time in the covariant form by writing dx alpha by d lambda. Okay, so this is the usual thing that we would have done in special relativity itself. Okay, so so of course, if you want to relate this to the non-relativistic expression, this thing what you need to show, or what you need to do, is to consider x naught to be a monotonic function of lambda, and then you could split this four-dimensional delta function into a spatial delta function times the temporal delta function, and then just carry out this lambda integral, which would tell you that you can replace uh, this expression uh, when you do a lambda integration. Then you need to use this delta function identity to replace this delta function as derivative of the argument. Okay, so argument of the delta function contains x naught n lambda, and that is the one which will be differentiated, because this is a quantity which is constant as far as lambda integration is concerned, and therefore this would give you d by d lambda of x naught n in the denominator. Okay, so if you substitute that, you basically get back the expression that we have written down for J0, because this quantity cancels here, and we get the uh, charge density expression that we have written down earlier. Okay, uh, one can do similar exercise for the current density, and in that case also you would see that you would get dxi by dt under this swap. Okay, fine. So there was some exercise that I mentioned, that this was also mentioned last time, I suppose. Uh, so what we want to do now is to generalize this setup to curved space, and one way to do that is to just covariantize the equations that we have. Maxwell's equations are tensorial equations, so you can replace etas by g's and partial derivatives by covariant derivatives, and that would give you an equation of this kind: g alpha beta d alpha f beta gamma plus g gamma delta times j delta is equal to 0. That is kind of expression where the j that we have written down this in this equation is the same j that we had written down earlier, except that that was special relativistic, and we need to kind of be sure that under general coordinate transformation, this quantity is invariant and or rather covariant, and therefore we need to put this factor of 1 over square root of determinant of g in this. Okay, so this expression would transform covariantly under coordinate transformation, general coordinate transformation. Okay, fine. So, since even in the Lorentz frame, this equation g alpha beta d alpha beta gamma plus g gamma delta j delta was a covariant vector. Okay, therefore, if this quantity was 0 in one frame, then it will be 0 in all coordinate frames which are related to this frame by general coordinate transformation. Okay, so all we need to do is to just check whether this equation is valid in, say, a locally inertial frame. And of course, in the locally inertial frame, it reduces to the ordinary Maxwell's equation, and we know that this equation is valid there. Okay, so therefore, this generalization of this equation uh, is valid in all coordinate systems. Okay, fine. This is an exercise where you basically write down J in the special relativistic form, which is the first expression for J alpha, which is something we had looked at some time ago, and we also took a non-relativistic limit. But what we want to do is to convert this expression into a general coordinate invariant expression. And what one has to show is that if you do a general coordinate transformation, then you need an expression like 1 over square root of minus determinant of g in the denominator for this entire expression to be covariant in the general coordinate transformation, that it should transform as a contravariant vector under GCT. Okay. Fine. So therefore, the general principle is that given an equation that represents kind of a correct equation in curved space for whatever formula that you had, say, in the Minkowski frame, is to do two things. First is to ensure that the expression is general coordinate invariant. So like the way we just talked about for J, that this expression is definitely Lorentz covariant, but you want to have the expression which is covariant under general coordinate transformation. So you need to modify that. So you have to ensure that the expression has covariance in the general coordinate transformation. So that is first condition. And the second condition is that if you take the special relativistic limit, that means if you are in a locally inertial frame, then you should get back to original equation whose generalization to curved space you are looking at. Okay, so and this is something that we uh, kind of checked. We claim that this equation has a tensorial property, and if you go to a frame in which G alpha beta is eta alpha beta, then the Riemann crystal connection inside D alpha would just vanish. Uh, that is what would happen in locally inertial frame, and then this equation just reduces to the special relativistic form. Okay, so there are two conditions that we used while generalizing this equation, same axis equation to curved space. Okay, fine. So this is the statement corresponding to the second condition that one is talking about. Okay, that you just when you go to locally inertial frame, it just reduces to the original Maxwell's equation. Okay, so the question would be that are these guiding principles sufficient to uniquely determine curved space generalization? And the answer is yes, provided we use both the conditions. Okay, and uh, this, of course, is a loaded statement in the sense that, like, you may not want to use both the conditions, and in that case, of course, the extension to curved space is not unique. Okay. Now, of course, the first condition is essential because first condition just says that it should be general coordinate invariant or general coordinate covariant object, and that is something which is essential because the entire setup for general relativity is based on invariance or covariance under general coordinate transformations of various quantities. Okay, so if you want to generalize some object, some equation to general relativity, it better satisfy that condition. Otherwise, like whole structure collapses because if the object is not general coordinate invariant, it is not even meaningful to compute anything in one particular frame simply because in some other frame it may just look totally different. Okay, so uh, clearly that is essential condition. One could ask a question: what about the second condition? Can we relax that? And the point is that if you do relax that condition, then all you would be doing is that you would be looking at a weaker equivalence principle than Einstein's equivalence principle. Okay. So, for example, if you relax uh, that condition, then you could write down an equation of this kind, and if you go to a frame which is the Minkowski frame. Okay, so remember I'm talking about Minkowski frame and not the local Lorentz frame. Okay, so there's a distinction between this because in the Minkowski frame R alpha beta would vanish, whereas in local Lorentz frame they may not vanish simply because the information about the curvature of space-time is a tensorial information, and therefore, even if in the local Lorentz frame you can bring metric to a flat metric form and connection to zero, the derivatives of connection may not necessarily be zero. And in that sense, rich scalar and rich tensor would be non-trivial. Okay, fine. So if you take a flat space limit, which is uh, kind of situation which what we have started off with, okay, then in that limit, R and R alpha beta would just vanish, and this equation would actually boil down to the flat space Maxwell's equations. Okay, so uh, in that sense, we would still be doing correct calculation in the flat space, but in the curved space, there is no unique way of generalizing this. Okay, of course, this would require us to abandon Einstein's equivalence principle, because Einstein's equivalence principle says that the equation should reduce to the special relativistic form even in the local Lorentz frame. Okay. Now this equation definitely is not going to reduce to that form, simply because R and R alpha beta would be non-zero, and therefore in the local Lorentz frame this equation is going to look different from the kind of equation that you would see in the Minkowski space or in the flat space. Okay, fine. Uh, yeah, so it's something I just talked about actually. Okay, so so this, of course, this new equation that we have written down, which involves Ricci scalar and Ricci tensor. Okay, this equation would imply that we can in fact obtain information about curvature of space-time by simply studying the motion of a charged particle in a sufficiently small space-time region. Okay, and and if that is the case, then this is clearly in contradiction with Einstein's equivalence principle, because Einstein's equivalence principle says that in a sufficiently small region, laws of physics in the curved space should just reduce to those of special relativity. Okay, so in that case, you shouldn't be able to figure out any information about the curvature of space-time. Okay, so if you are going to stick to the Einstein's equivalence principle, then you would be essentially forced to set A and B both to zero, where A and B were the coefficients of the Ricci scalar and a square of Ricci tensor term in this equation. Okay. On the other hand, if you say that, like, okay, I don't want to stick to Einstein's equivalence principle, then of course you could study this equation. You could try to put bounds on this with respect to whatever is experimentally observed. Okay. Now this is something we had discussed, but let me again go over this particular point that suppose you look at one particular term. Okay, so this is just for simplicity. Suppose you look at only the Ricci scalar term and you say that the Ricci scalar is of order 1. Okay, then we need to, of course, qualify what we mean by something like Ricci scalar being of order 1, because it's a dimension-full quantity. It's a derivative. It involves two derivatives of the metric. Okay, so it has effectively dimension 2 with respect to the space-time dimensions that we have defined. Okay, so when you say a dimensionful quantity is a number, you need to say that it is a number with respect to some unit. This thing. So it's like if you are measuring a length, you cannot say that the length is 2 unless you mention whether it is in centimeters, inches, meters, whatever. Okay, so you need to give a unit of measurement for that. Okay, in the theory of gravity, there is not much of a freedom that you would have. You need to define some quantity which has dimension coming from the fundamental variables that are used in defining the theory of gravity, and that involves three fundamental constants. One of them is Newton's constant, speed of light, and the Planck's constant. And you can construct some quantity called Planck length, which is defined as g Newton times h bar upon c whole to the half. Okay. Now remember that the Ricci scalar came with a coefficient a, and this coefficient should have dimension which is opposite of the dimension of the Ricci scalar, so that this expression, which is 1 plus something or other, okay, 1 plus ar plus whatever, okay, this quantity is of course dimensionless, so therefore each one of them should be dimensionless, and therefore it determines the dimension of A to be proportional to length squared. So we should be able to write down the coupling A in terms of the Planck length squared. Okay. Now it turns out that the Planck length is a very small quantity actually. It is something of the order of 10 to the minus 33, 34 centimeters. Okay, and if that is the case, then you would want a Ricci scalar to be sufficiently large for you to be able to experimentally detect terms of this kind. Okay, now uh, the quantities that are required are something of the order of Rich's scalar being of the order of 10 to the 60, such that it will offset something of the order of 10 to the minus 66, 68, something of that type, to get some result which is of the order of a few parts per million. Okay. Uh, well, our experimental capabilities are better than that. We can do something of the order of 10 to the minus 10, 20, even 10 to the minus 15 or something, to measure quantities of that scale is still possible experimentally. So in principle, it may not be 10 to the 60, it could be something of the order of 10 to the 50, but nevertheless, this order curvature is very large, and definitely it's not, we do not see this kind of curvatures in the neighborhood of, say, our planetary system, for example. Okay. Uh, Possibly this would happen closer to black hole, and in fact, not even closer to the horizon of the black hole, particularly if you are looking at astrophysical black holes. The curvature in the neighborhood of the black hole horizon is pretty small actually. You really have to go across the horizon and close to the singularity to see numbers of this kind. These things. So, okay, so in that sense, if you want to do some local experiments to detect factors of these kind, it may be a reasonable thing to assume that Einstein's equivalence principle is true, and for all practical purposes, and ignore terms of this kind. Okay.
Sir,
Fine.
would you go
Yes.
a slide above?
Yes. Sure.
I mean, I understand that forming a dimension out of these constants is fine, but
Hmm.
why would we expect that the equivalence principle would break down particularly at this scale only?
No, no, no. Equivalence principle wouldn't break down at this scale. Equivalence principle can be tested at this scale with our experiments. It could break at any scale. Okay.
Sir,
Is the point clear? Yeah, yeah.
I
I'll
mean,
take the other.
we are
Yeah,
sort of considering the importance of the magnitude of LP, right?
that is right. Yeah, because because of our experimental capabilities. See, the point is that, like, that is why I'm saying that, like, it is reasonable to assume Einstein's equivalence principle, because there is no experiment that we can do which would allow us to distinguish uh, whether there is a term which is 1 plus a times r, or is it just 1. Okay. uh, so but it has nothing to do with uh, LP being very small. I mean, well, okay, I shouldn't say it that way. It definitely has something to do with LP being very small. But the point that we are trying to say is that, like, our detection capabilities are not as good, and that is why we want curvatures large enough so that our detector would be able to detect. Now, uh, suppose you are looking at space-time where the curvature is not this, but curvature is of the order of, say, 10 to the 10. Okay. In Planck unit, of course, this thing. Then you will have to upgrade the detector technology to be able to pick up factors of that, effects of that kind. Okay. And as I was mentioning in last lecture, that LIGO is actually kind of doing detections at very high precision, something of the order of 10 to the minus 26 centimeters or something like that. So, uh, I mean, it may be able to reach something of the order of 10 to the minus 30, 40 years, some such thing. Particularly, there's some other experiment which is proposed called LISA, which is supposed to be uh, uh, microsome interferometer in the sky, actually, with 3 satellites and so on. In that case, of course, one may be able to scale it up a lot. So it's more like a statement about uh, it's more like a statement about the uh, our capabilities than whether the equivalence principle is correct or not correct. In fact, like, if you say, for example, if you do string theory, then Einstein's equivalence principle is not true. It's you do have higher derivative corrections to Einstein's action, and therefore to equations of motion, and therefore you are not actually obeying Einstein's equivalence principle.
But those are like something like quantum mechanical corrections, right?
No, they are just stringy corrections. that instead of the object being point-like, it is an extended object, and that itself gives you higher order corrections.
Yeah, but I mean, that is not to say that something is wrong with the flat space picture itself.
No, no,
Like,
no. That's not what it is saying. It is just saying flash space picture is fine. Local Lorentz picture may be different. Is it
okay.
okay? So
Also,
yeah,
this another issue, like it also should come up in like even special theory that laws of physics, like equations of physics,
yeah,
we may not always be able to identify some four vector or something. Like in Maxwell's equation, we can sort of claim or declare that a mu acts like a four vector, and
yeah,
and therefore we can generalize the equation first to special theory, then to this general
uh,
theory.
yes,
But
yeah,
in equations where we only know some empirical form or something, like
yeah,
even a simple law like Ohm's law, which
yeah,
even if we assume to be true for a material, like exactly ideally true, we
yeah.
cannot sort of generalize it to a moving frame, and that we cannot even do for Galilean transformations for that matter.
That is right. But that is because many of these results are approximate results, right? Galilean
Yeah,
transformation is an approximate result with respect to special relativity, right? So therefore, you cannot generalize Galilean transformation straight away. But if you say that if you do, you have better understanding of these results. If you do approximation of that to certain situation, then you derive various laws.
yeah.
That is fair
Even
enough. Yeah.
like can we? I'm not sure, but can we generalize something like Navier-Stokes equation or something?
Yes.
Yeah,
Yes. Eminently. There is a relativistic Navier-Stokes equation, uh, and in fact, there has been a lot of work of how to relate fluid dynamics to gravity, and a lot of results related to the black hole physics can be actually derived from relativistic fluid dynamics. Mm. In fact, this idea goes back to uh, late 60s, around 69, 70. There was a proposal by um, uh, Kip Thorne and some other and collaborators that where they say that the horizon of the black hole can be thought of as a membrane, and the the membrane degrees of freedom, the fluctuation of the membrane can be mimicked in terms of some kind of a two-dimensional fluid, I mean 2 plus 1 dimensional fluid, and that idea was called membrane paradigm, which is very much in the vogue. Actually, a lot of results can be derived using the membrane paradigm and using relativistic fluid dynamics. In fact, when you do cosmology, for example, you say that cosmology, the energy momentum tensor in cosmology is written in terms of perfect fluid or pressureless fluid or and stuff like that, right? So you do actually assume the energy momentum tensor on the right hand side of Einstein equation to be a tensor coming out of certain like kinds of fluids, right? So you do actually use those.
okay.
Okay, Aman also had a question.
No, it was Shukalpo. I just
Oh,
Yeah, hello.
oh, I see. Okay, Sukalpa.
Hello.
Yes, yes,
Yeah, sir. In the flat space time, we saw that if a particle moves with a constant velocity, it does not radiate.
yes.
How does those things, generalize in this case?
Well, well, in this particular case, you are looking at a, uh charged particle in a curved space. Okay, so in the curved space, of course, it would. I mean, because of curvature of space time, it would accelerate, right?
Yeah, then won't it
Yeah, it would
radiate?
radiate. Yes, of course, it would.
Then,
Right?
won't it break the equivalence principle, right? Like, say, I am in an accelerated frame, a charged particle is also with me. Now, that feels a back radiation while I don't. Then,
No, no, no. Why would it?
So suppose me and a charged particle both are in accelerated frame, then I mean
Yeah,
everything should be same for both of us. But that particle feels a back radiation, while I
that is
don't.
right.
So
Yeah, yeah, definitely. So yeah, so it could happen. In fact, uh, that so like for example, you can think about a situation where an object is kind of accelerating away from you. Okay, and which I mean, in your frame, you are always the inertial observer. So you just worry about the other object being accelerated. Okay, and because that object is accelerating, it would continue radiating at some point. But if it continues to accelerate all the time, then at some point its radiation wouldn't reach you. Okay, simply because of its acceleration.
okay, then if
So
we think it, I mean in the other way that a gravitational field is equivalent to an accelerated frame. So if suppose I am on Earth now with a charged particle.
yeah,
Now, I mean, it is equivalent to an accelerating frame. So, I should observe this charged particle to radiate all the time, right?
no, not in your frame.
Why? Because those are equivalent.
No. See, that is the point. That the radiation. Okay, so you have two objects sitting around doing nothing. Okay, in the same frame. Okay, with respect to some third frame, the object is accelerated, right? Now, out
Yes.
of out of these two objects, one of them is charged object, the other one is not. Okay, right? So an accelerated observer would say that like a neutral object would sit around and the charged object would radiate, right? Is that okay?
Okay. So, you are saying that I
Right?
mean, some other observer will observe that.
Yeah. Other observer would think that this is what is happening. You wouldn't see it. Okay. So how does this happen? This happens because there is a gravitational field. Okay. There is a field acceleration which actually emits a photon. Okay. Emits electromagnetic radiation. Okay.
Okay.
So, so there is an interaction of electromagnetic radiation with gravity, okay, and it is the gravitational field which will emit the electromagnetic radiation, which will make that observer feel that this particle is actually radiating the uh, electromagnetic radiation. Okay, so
Okay.
it's a kind of more complex system because you have to take everything into account when you write down Einstein equation. You don't look at only charged particle. You also have an electromagnetic field along with it, and it's a combined system that you need to look at. Okay.
Okay.
Okay. Any other question? Okay. So we will assume that for all practical purposes, Einstein's equivalence principle is fine. Okay, and we'll continue using that uh, until we kind of feel that like okay, we need to go beyond that. Okay. So, for example, if you want to kind of propose a theory of quantum theory of gravity, you may find that like okay, Einstein's theory is not so easy to just quantize just like that. Okay, and you may want to write down more general description in terms of different kind of degrees of freedom, and those different degrees of freedom may actually require you to assume weaker equivalence principles than Einstein's equivalence principle. In that case, you may want to attempt and see whether with some weaker assumption you could make some consistent theory of quantum gravity. If not, then of course you abandon the program and not abandon Einstein's equivalence principle. Then get back to the original one and try again. Okay. So of course there have been, as I mentioned earlier, there have been dozens of attempts to try to get quantum theory of gravity, and you know not many of them have actually succeeded. All of them went up to some distance, different reaches they had, but haven't succeeded completely. Uh, and as I said, with my prejudice with string theory, I would say that like at least that is by far the best attempt to give you some quantum description of gravity. Uh, but it is, I mean, the jury is still out on getting exact quantum theory of gravity. By exact, I mean not exactly soluble, but at least the theory which makes sense, uh, and where you can do computation and get finite answers for any problem that you would want to ask in gravity and with any kind of gravitational background. And in string theory, there exists a certain class of backgrounds about which you could study perturbative quantum gravity and show that it makes sense completely, but it is not totally general as yet. Okay,
Uh,
so yes, please.
I sort of missed the previous point. What's the problem of accelerating charge particles? So just to clarify,
Yeah,
if I have two observers
yeah,
and one charge particle,
yeah,
and one of the observers and the charge particles are free falling in gravity,
yeah,
and the other observer is like still, like
yeah,
sort of
accelerating.
accelerating against gravity.
Yeah,
So the still observer will see some radiation, right?
yes, absolutely.
And if
Yeah,
I and the other one won't, the free
yes,
falling one.
yeah.
And
So
if I
you are,
reverse, yeah,
yeah,
and
you are carrying the charge particle and falling freely. You won't see the
yeah,
radiation.
yeah. And if I reverse the situation that I and the charge particle are still against
Yeah,
accelerating against gravity and staying still at a point,
yeah,
and one observer is free falling,
yeah,
then the free falling one again will see some radiation,
yes,
but I won't.
yeah. You won't. In both cases, you won't. Yeah.
Yeah,
So it's like, you just try to kind of look at the picture in the following way. You try to you know uh, take, say, a hydrogen atom problem. Okay, we are not doing hydrogen atom, but just to get a picture. Okay, you have this 1/r potential which is going down, right? Okay. Now you think of this 1/r potential, minus 1/r potential, really. That is the kind of thing you think of now as a gravitational problem. You have minus 1/r gravitational potential, and you started off with a fixed energy. Okay, right? Now, if you are a freely falling fellow, okay, then with a fixed energy, you actually would be having uh, effective energy that you would have is larger and larger as you start falling in, right? Is that
yeah,
okay? Because the potential is going down, so the kinetic energy available for you is larger and larger, right? Now is that effect is actually gravitational field effect, because gravitational field is falling, and therefore your effective kinetic term is going up, right? Okay. So this increasing gravitational field is actually the one which is responsible for emitting light as the object falls in. Okay. And so the asymptotic observer, or observer at a fixed location accelerating to keep his or her position fixed, okay, would see a radiation coming out of this additional kinetic energy that the gravitational field has generated for the freely falling particle, okay, in terms of light emitted by the particle. Okay. Whereas if you are with the particle falling, freely falling in, you wouldn't even see this, because both of you are kind of gaining energy at the same rate. Okay. So the acceleration effect of a charged particle is a coupling between electromagnetic field and gravitation. That is the thing that the observer would see. Okay. That is what I was telling Sukul.
So, but
Yeah.
this changes in the presence of curvature, right? Because like when we are writing this Maxwell's equation in
Yeah.
curved space-time,
Yeah.
we have a curvature term there.
Yeah.
So this wouldn't hold true everywhere.
No, this potential is actually the effect of curvature. No, this 1/r potential is the curvature effect.
I mean, locally, if we are talking about a charged particle, this 1/r potential can be like if I go to a particular frame where the space is locally flat
Yeah.
up to a curvature term, uh,
Yeah.
we would think that this like the charged particle behaves as if it were in flat space time. But since we are writing this Maxwell's equation in
Yeah.
actually the space time is curved there,
Yes.
and there is some curvature term there,
Yes.
which cannot even be neglected when we are in a locally flat space, like
Yes.
a locally flat frame.
Yes.
So curvature term would be there every always.
Yeah. Yeah. Certainly.
So
So
like
yeah.
that's how what I'm saying. It need the charged particle need not follow equivalence principle there.
No, what has this got to do with equivalence principle?
Because I mean, equivalence principle would say that the charged particle follows in a locally flat frame. I would see that the charged particle falls freely,
Yeah, yeah.
but
It would,
that wouldn't hold true.
it would if there was no electromagnetic field, right? I mean, the particle has a charge has no consequence if the electromagnetic field is not there, right?
But but the particle itself is producing some field, right?
Yeah, that is right. So, so that that would require you to have another observer to see a charge. See, Lennard-Wishart potential that you want to study, generated by an accelerating charge particle, requires an observer who is not in the same frame, right?
Okay.
Right.
Yeah.
So, yeah, so the other observer would see it, okay, but it could be an effect generated by a coupling of gravity with photon, actually. I mean, electromagnetic field.
Also,
Yeah.
you said that when the particle is falling and the observer is at still, the
Yeah.
photon emitted that the radiation emitted that the other observer sees is due to the gravitational drop in potential.
Yes. Yeah.
So, and how do we explain it the other way? Like if a observer is freely falling inside and the particle is at still,
Yeah.
like, so what would you like analogously say here, that where is the radiation energy coming from or something?
Yeah. No, actually, in that case, with respect to the observer, it is gaining energy, right? The particle which is stationary is actually gaining energy.
In its frame, yeah.
Yeah. So it is soaking up the radiation and not emitting.
Yeah, but like, what would the observer see? Will they see photons or not?
Yeah. I don't know. Maybe. Yeah. Yeah, I don't know offhand what it will see, but it would probably see that. I mean, it will see some energy conservation thing, that it would see that the electromagnetic field energy is kind of reducing. You have to set up a problem which involves electromagnetic field, particle energy momentum tensor, and gravitational field, right? So
Yeah.
there's an electromagnetic energy momentum tensor, particle energy momentum tensor, both coupled to gravity. And you would see that the trade-off is in one situation, the trade-off is from energy momentum tensor of particle to electromagnetism, in which there is a radiation going out. In the other case, there is an energy momentum tensor from electromagnetism trading off energy to the particle, in which case the energy is being soaked up from the electromagnetic field. Okay, so
Yeah.
the total energy is of course conserved in that setup locally, definitely. Okay, but the trade-off goes in the opposite direction.
But this should be exactly solvable, right?
Yeah, it should be exactly solvable. Yeah, I mean, at least, well, exactly solvable in the sense, if the space-time is reasonably good, in the sense that metric is not too horribly complicated, it should be solvable. You know, if somebody gives you a terribly complicated metric, then of course, it may be a very hard calculation. But say, for example, say Schwarzschild metric, it should be possible to do this computation. Okay, and it's a good metric to do this. Okay.
So one more question.
Yeah.
Let's say the charged particle was rotating around a black hole. It is on a trajectory that is freely falling. So
Yes.
we should expect that after some time it should fall into the black hole
Yes.
because it is radiating.
Yes, it will radiate and fall. Yeah, unless it finds Bohr orbit for itself.
Okay, yeah, but
Okay,
the thing is, if we are if we are in the same frame as the charged particle, then we are not expecting that it is radiating there.
yeah, that is right. But you're still
So,
falling in, right?
uh, but uh, initially it was like following a free particle trajectory,
Yeah,
like freely falling trajectory.
yes.
So, like in that frame, the particle is behaving like a neutral particle. So I should not see any deviation between the charged particle's trajectory and the neutral particle's trajectory.
Yeah. So, so yeah, I understand what you're getting at. So the point is the following: that you started off with a. Okay, so let's get back to the equation. Then you can kind of see what is happening with it. Okay. Uh, yeah. Uh, doesn't matter. Yeah. So I can kind of. Okay. See, the point is that like this equation is a tensor equation, right?
Yeah.
So the thing is that like if you started off with the charged particle and if you are in a kind of freely falling frame, okay, then initially of course nothing is happening. But even in your frame, you would see that the charged particle is coupled to electromagnetic field, right?
Yes.
And now if you are in a freely falling
That
frame, yeah,
that electromagnetic field would be solely due to that charged particle itself,
due to the charged particle itself,
because
yeah,
there's no other. Yeah.
there is no other
Mm,
electromagnetic field, yes, exactly. But it is that
yeah.
that electromagnetic field also couples to gravity, right?
Okay. Yeah.
So, so what I was saying, in, uh, as an answer to say Kaustub's question was that in the gravitational setup, the total energy of the electromagnetic field and the energy of the particle is conserved. Okay, but the charged particle could trade off energy to the electromagnetic field and fall in. Okay, and that you should be able to see in your own frame because this is a tensorial equation. Okay, that if the charged particle is trading off energy to its own electromagnetic field, okay, you should see the charged particle kind of uh, having a relative motion with respect to you, and it would fall in faster than you do. Okay, so this
Okay.
is equivalent to the statement about the black hole thing. Remember that, like if you want to, if you are trying to kind of okay, let's put it in the following way that if you find that you are following a trajectory which is going straight into the black hole, okay, then the question would be as to what is it that you should try to do to you know I mean live longer, you know and the answer is that like that if you are freely falling, then you are following the geodesic uh, path, okay, and that is the path which is kind of has the least action, okay. Anything extra you do, you would actually fall faster because you're you know in a state which is higher energy state than the geodesic state, okay. And therefore is exactly same thing will happen with charged particle, that if the charged particle, if the particle was neutral, it wouldn't be doing anything besides freely falling with respect to gravity, okay. But if it had additional force acting on it, then it would definitely trade off energy between that electromagnetic field in this particular case and fall faster, okay. And that should be observable because the equation is tensorial.
Right now, there is no external force, right?
There is no external force, okay. But there is a coupling of the electromagnetic field generated by the charged particle. So charged particle and its own electromagnetic field both couple to gravity, right? Okay. So the total energy of, as we'll go ahead and we'll see that the total energy momentum tensor is the energy momentum tensor of electromagnetic field plus energy momentum tensor of charged particle. It is this quantity which is conserved. Individually, they are not conserved. In fact, we will see the non-conservation of it actually. that okay?
Yeah. Okay.
Okay, so where are we?
Sir,
Yes.
so is the existence of a particular particle, I mean, frame dependent? Like you said that in the
No,
particle frame we will not see that there is any photon.
no, no, no. No, no. Existence of which particle? Photon?
Yeah.
Yeah. Well, existence of photon could be frame dependent, right? I mean, it's like uh, if you are in special relativistic frames, okay, you wouldn't see. Uh, I mean, you. I mean, your frame and charge particle frame are inertial with respect to each other. You don't see radiation. Okay, you accelerate yourself when you see the radiation, right? So existence of photon could be a frame dependent quantity, not within special relativity, but of course in accelerated frame it is true.
Okay.
Yeah. Okay. So given that we are designed to kind of work with Einstein's equivalence principle, given because of a lack of any possible way of seeing the violations of it, we will kind of continue using that. And the simplest way of generalizing any known equation to a general coordinate invariant equation is to replace ordinary or rather partial derivatives by covariant derivatives. Okay, and that is what would give us the Klein-Gordon equation written in this particular form. Okay, although you may not have seen it in this particular form in a covariant way because d beta could have been just ordinary partial derivative and it would be same as this equation. Okay, because for a scalar field there is no action. The Riemann-Christoffel connection doesn't act on a scalar. Okay, fine. So this equation, of course, satisfies the same conditions that we were imposing earlier. Namely, in the local Lorentz frame, it would reduce to the flat space Klein-Gordon equation. And of course, this is general coordinate invariant expression because the left-hand side of this is a scalar with respect to general coordinate transformations. Okay. So therefore, if this equation is true in one frame, it would be true in all other frames. So that kind of pretty much settles the form of this equation in curved space-time with Einstein's equivalence principle. Okay. So now we could ask a question that like, okay, what about doing this for gravity? Okay. So we could ask, go back to non-relativistic physics, and that is a place where we have Newton's law of gravitation. And since various laws have been generalized to special relativistic form and then effectively to general coordinate covariant form, we could ask a question that can we write down Newton's law in a general coordinate covariant form? Okay, and the first problem is that the equivalence principle doesn't help us at this in this case because it tells you that if you are in a local Lorentz frame, then your equations of motion would just reduce to special relativistic form. And if that is the case, then you wouldn't know how you would write down Newton's law um, in the special relativistic form. Clearly, special relativistic equations tacitly assume that there is no gravity, and therefore Newton's law of gravitation was something which was not part of the special relativistic description. Okay, fine. Uh, so the other thing was that, like, besides just generalizing Newton's law of gravitation, we could have said that, like, okay, we can take another point of view, and that is to say that the space-time metric carries information about the curvature of space-time, and if the curvature of space-time is related to gravity, which is what is the proposal, then we might as well ask what is the equation that the metric satisfies. Okay. Uh, well, that also has no guidance simply because in the flat space-time, the metric was given by the Minkowski metric and it did not satisfy any equation. And it did not satisfy any equation simply because all entries were the preferred choice of the form of that metric. All entries were constants and therefore it would have even satisfied the first order differential equation to be equal to 0, for example. Okay, and it doesn't seem like giving us much of a guidance as to what kind of equation of motion that a metric would satisfy, which could be generalized such that it is general coordinate covariant. Okay. So given that we don't have direct guidance, we are basically going to use a kind of indirect method as to look at equations that we know, from which we can learn something and derive equation which is consistent with Newton's law of gravitation. Okay, so so let's start with electromagnetic theory. And electromagnetic theory, we have an equation where some function of derivative acting on the electromagnetic field or electromagnetic potential is proportional to the source. Okay, charge particles generate some kind of charge density, current density, and so on, and it couples to this equation. Okay, so we could claim that, like, okay, we can just generalize this equation and say that, like, similar function acting on metric is proportional to the source. Okay, and only condition that we can impose on this equation is that if you try to determine this equation, then in the non-relativistic limit, it better give us Newtonian gravity. Okay, if you want to claim that G alpha beta is the correct representation of curvature of space-time and which mimics the gravitational field. Okay. So what we will try to do is first settle what are these sources, and then we settle what this equation on the left hand, what is the left hand side of the equation. Okay. Fine. But before that, let's kind of do a small detour into this non-relativistic physics and just kind of get an idea as to what is it that we would be reducing our equation to, just to check with the Newtonian gravity. Okay, so in the Newtonian gravity, there is a Newtonian gravitational potential which satisfies the Poisson equation, and that means Laplacian acting on the gravitational potential is equal to the mass density. So rho is the total mass density, and you want to solve this equation corresponding to various kinds of mass distributions. Okay, you may want to have point mass, or you may have bunch of point masses, or stuff like that. Okay, fine. The first hurdle that we encounter here is that mass is not a conserved quantity in relativistic dynamics. Okay, forget about general relativistic description. Even in special relativistic dynamics, mass is not a conserved quantity, but energy is. Okay, so what we would want to probably say is that in the non-relativistic limit, it is the mass, but maybe the relativistic description of this should have been energy. Okay, now the problem with energy is that energy itself is not a kind of Lorentz invariant object. It is in fact a component of a 4-vector, which is what you call the momentum 4-vector, which is written as P alpha, which is m times dx alpha by d lambda, where m is the mass of the particle. Okay, so so energy may not be a right thing to use because that is not a relativistically covariant object. So you actually may want to use the momentum 4-vector. Okay, now if you want to use a momentum 4-vector, then you would be kind of worried about what is the index structure on the left hand side of this equation. Oh, when I say mass is not conserved, I mean that, like, you know, this is a question in the chat. When I say mass is not conserved, I mean that, you know, the rest mass is conserved, but if the object is moving, then it has a moving mass which is not a conserved quantity. Okay, it keeps changing. Depending on which frame you are, the value of mass is different. Okay, and gravitational field couples to the total mass, right? So therefore, it would couple to whatever mass that the gravitational field would see. If the object is stationary, then it will see rest mass. If the object is moving, then it will see its moving mass, and so on. In that sense, it is not conserved. Okay. Fine. So, so we would like to ask a question that, like, you know, what kind of form of this equation that we would want to have, such that a quantity on the right hand side is a covariant quantity. Okay. So it turns out that, like, momentum 4 vector is also a part of something which is bigger, and that is that it is actually uh, a conserved charge corresponding to a conserved quantity called the energy momentum tensor. Okay, energy momentum tensor is a second rank tensor, and therefore its conserved quantity is the first rank quantity. In electromagnetism, you have a first rank conserved current, J alpha, and therefore the conserved quantity is a scalar quantity, okay, or zeroth rank quantity. Okay, in this particular case, you have a T alpha beta, and it satisfies the conservation law, and and the corresponding conserved quantity would carry only one index, not both. Okay, so P and alpha is a kind of quantity that you would write down for nth particle, which is the conserved momentum 4 vector for that particle. Okay. Now, in this particular case, of course, you are looking at a setup in which you are writing down the energy momentum tensor for a particle following a particular trajectory, and its kind of alpha 0 component, which is basically the momentum 4 vector piece, is written in this particular form. Okay, the corresponding current density would be written as alpha I, and that would be proportional to the same expression times the velocity of the particle, and that's what is this expression. T alpha I would be is pretty much analogous to what we did for the charge density and current density for the electromagnetic field for the charge particle. Okay. So we can generalize this and write down a covariant expression for this, and the covariant expression would be something like T alpha beta, which is equal to, you write down the momentum P alpha in this particular form as m times dx alpha by d lambda, to write down this entire expression as m times dx alpha by d lambda times dx beta by d lambda. Okay, so all these pieces can be put together to write down this entire expression. Okay. So first thing that you see is something which is obvious, and that is it is symmetric in alpha beta. Okay, and that is something which is quite good. If you try to write down, say, actions for point particles or for fields, and try to derive energy momentum tensor using what is called the Noether prescription, typically the energy momentum tensor that you get by following that prescription is not symmetric. Okay, T alpha beta obtained by Noether prescription, which is, if you remember, it is written as delta L by delta derivative of the field times the derivative of the field minus eta alpha beta times the Lagrangian density. That is how the energy momentum tensor is written. You may have probably already done it in quantum field theory. That energy momentum tensor generically is not symmetric. Okay, whereas the kind of energy momentum tensor that you encounter in gravity is manifestly symmetric. Okay, and that is one of the reasons why the best way to get a symmetric energy momentum tensor is to kind of make the metric dynamical in the action, and then differentiate with respect to metric, and then in the end set the metric to be equal to, say, Minkowski metric. Okay, that is one nice way of writing down the metric, writing down the energy momentum tensor in naturally symmetric form. Otherwise, what one needs to do in quantum field theory is to write down what is called an improved energy momentum tensor, or what is called a Bell-Infante tensor, which is related to the original tensor by a total derivative term, and that original tensor derived from the Lagrangian plus a total derivative term, which is of course conserved, like the original tensor is conserved, but that is a symmetric object. Okay, so yeah, so in this particular case, you naturally get energy momentum tensor in a symmetric form. Okay, so you can check that this energy momentum tensor is second rank contravariant tensor under Lorentz transformations, and for a free particle it is conserved. Okay, in the Minkowski space, of course. Okay, so so this is just a statement of conservation of energy and momentum for a free particle. Okay, but suppose this particle is moving in an electromagnetic field. Then your equation is different. In this case, you get that you find that the acceleration is not equal to 0, but that is equal to the Lorentz force. Okay, and if that is the case, then this statement that you have to show that energy momentum tensor is conserved for a free particle in Minkowski space, not true. Okay, in fact, what you find is, because of this equation, what you find is that derivative of the energy momentum tensor, okay, or rather divergence of the energy momentum tensor, is not equal to 0. It is proportional to the electromagnetic force. Okay, and that is just as well, because there is a trade-off of energy between the electromagnetic field and the charged particle, and it better show in the conservation law. Okay, so what we will do is we will write down this expression in a little nicer way. In this expression, if you forget about this eta times f piece, okay, and look at everything else, that is a quantity which was the current covariant current that we have written down in special relativity. Notice that there is no 1 over square root of determinant g, because we are still in the Minkowski space-time. Okay, so you can replace this entire sum and integral by just the corresponding current of the bunch of charged particles. Okay, and therefore you get an equation which looks like the divergence of energy momentum tensor is proportional to f times j. Okay, now at this place what we will do is we will use Maxwell's equation. Okay, so Maxwell's equation, remember what j was proportional to divergence of f. Sorry, I should have probably split the screen instead of doing this. But yeah, I'm sure you know this. Okay, so we are going to use this equation, j is equal to the divergence of f, and just plug it into this. Okay, so just a sec. Okay, so here's the equation, and we will use j, we'll trade off j and write it in terms of electromagnetic field. Okay, so here, I should not have gone. Here's the equation. Okay, so you just take this and substitute it into this, and you get the divergence of T to be this quantity, which is same, and J is replaced by this entire expression, okay, with a minus sign. Okay, now you can check that this expression is actually a total derivative. Okay, etas of course don't matter because they are all expressions with constant entries. And so you can show that this entire stuff can be written as del mu of some quantity. Okay, and you can check that the expression that would give you this quantity is this energy momentum tensor. Okay, so this is what you would call a electromagnetic energy momentum tensor, and that is written in this particular form. Okay, there are multiple etas sitting around just to ensure that the indices are correctly contracted. Like for example, eta rho sigma is just contracting these two indices, and this alpha gamma beta delta are just taking care of gamma delta indices and writing it in terms of alpha beta. So it's just that the contractions here and the contraction here are different. Okay, that is important. Okay, so yeah, so what you see is the following, that the first thing that we saw was the particle energy momentum tensor was not conserved. Okay, and it satisfied this equation. Okay, on the other hand, electromagnetic energy momentum tensor, which is written in this particular form, okay, is also not conserved. Okay, so you find that would give you this expression. Okay, but if you add these two, okay, then you find that total energy momentum tensor is conserved. Okay, so that is the conservation law of the total energy momentum tensor. So there would be an energy trade-off between the electromagnetic field and the charged particle, and whether that electromagnetic field is external or the charged particle has created that electromagnetic field, there is a trade-off between them, no matter how the electromagnetic field is produced. Okay, fine. So any questions at this point? Okay. So let's go ahead and try to find out how does the energy density of the electromagnetic field would look like. So for that, we can go back to this form of the energy momentum tensor, this particular form, that it is ff minus 1/4 times eta alpha beta times ff. That is the kind of expression. Okay. And just substitute alpha beta to be 0 0 in that expression. So you have to kind of check what are the expressions. There are like 3 etas sitting around, but there was alpha, gamma, beta, delta kind of stuff. So, but eta is diagonal, so it will set gamma and delta to be equal to 0. And in this particular case, there was alpha beta which was 0. So yeah, maybe I should just give me a minute. Yeah, yeah. Okay. So if you substitute alpha beta equals 0, this forces gamma delta to be 0. That is what is this expression. Here it will just set eta alpha beta to 0, but eta alpha, alpha beta to 0 in eta alpha beta, but eta 0 0 is minus 1. That's why it flips the sign here. That's why it's plus. Okay. And then, of course, all you need to do is to kind of split rho sigma and all these mu, nu, gamma, delta appropriately to write down all pieces. Okay. Once you do that, then you notice that you have f0i factors. Eta ij will set I is equal to j. So this f0i is like electric field. Okay. And fij is like magnetic field. Okay. So so you can check that these quantities put together gives you the okay. So maybe I should kind of state at this point that like fj0 is of course minus f0j. That is the kind of thing which would kind of flip sign for you. And if you take all these factors together, you get half e squared, and this factor will give you half b squared. Okay. So total energy of the energy density of the electromagnetic field is just half of E squared plus B squared. Okay, which is of course what we call Hamiltonian. The Lagrangian is of course expression involving the same quantities except there is a relative sign. It is half E squared minus half B squared. Okay, that's pretty much tells you that E is like the momentum and B is like the potential. So P squared minus potential versus P squared plus potential. Okay, fine. So when we are going to write down the equation for gravity, then we don't want to write down a quantity which is not conserved, but we want to write down a quantity which is conserved. Okay, so therefore what we will do is we'll write down a total energy momentum T alpha beta, which is a electromagnetic field energy momentum tensor plus the energy momentum tensor of the particle. Okay, and what we have seen so far is that both these energy momentum tensors, they are all written in terms of etas and stuff like that. It's like an expression like this. Okay, are covariant under Lorentz transformations. Okay, what we want to do is to elevate these fellows so that they are covariant under general coordinate transformation. Okay, and here is the covariant as form of both the energy momentum tensors. Okay, so so T alpha beta, which is a particle energy momentum tensor, I forgot to write the minus sign here. But yeah, is basically that you add 1 over square root of minus determinant g factor. Rest all is something which is the same as what we see in the special relativistic form. Whereas in the case of electromagnetism, you replace all etas by g. Okay, and that pretty much gives you this form. Okay, this should have been F. Okay, I'll correct this. Both corrections need to be done. Okay, so what we want to do now is to kind of replace the Lorentz covariant expressions to general coordinate covariant expressions, and then once you have the as general coordinate covariant expression, then because they are second rank symmetric tensors, symmetric is not important, but because they are second rank tensors, they would be covariantly conserved. Okay, and not it's not the partial derivative acting on it is zero, but the covariant derivative acting on T alpha beta would be zero. Okay, fine. So now, of course, this expression itself is the left hand side of that is a contravariant vector. Okay, should I say contravariant vector? And because it's a contravariant vector set to be equal to zero, and in the local Lorentz frame, we know that that would have been just partial derivative acting on T alpha beta equals zero. The conservation law would be true in all frames simply because it's a tensorial equation. Okay, fine. So what you so here's an exercise where you show that the conservation of energy total energy momentum tensor can be written in this particular form. Okay, so it requires kind of doing some jugglery with the indices. You know that the indices can be raised and lowered using metric. It's kind of an easy exercise. So what I'll do is I'll stop at this point. We'll kind of take over this, because what we have done so far by determining this form of the energy momentum tensor, T total to be T electromagnetic plus T particle, and T electromagnetic being this modulo typos, and T alpha beta being this modulo again typo, this thing. So we have essentially fixed what would be the right hand side of this expression. We'll have to go back again to Newton's law, which was the Laplacian acting on the gravitational potential, and what we have done is we have converted rho to a second rank tensor, second rank symmetric tensor. We want to ask a question: how do we settle the left hand side such that that is also a second rank symmetric tensor? Okay, and so that is what we will do in the next class. Okay, any questions?
So I would like to talk with you once the others have left.
Okay. Okay, but any question right now? Maybe you could take those first.
Sir, I have one more question.
Yeah.
Can you go back to the equation that you wrote for electromagnetic fields, the Maxwell's equation?
Yeah, just a second. Okay. This one?
Mm, yeah, the covariant form.
Covariant form, okay. Jump too much, I think. It's not scrolling, it's not scrolling fast enough. Sorry. Yeah.
This.
Yeah.
Yeah. So when this is a coupled equation, right? In
Yes.
F. So when we are solving, let's say we were solving it, this equation for 0, the charge is 0, free field solutions,
Yeah.
let's say. Then